When Jim talks to us about the work he does at NASA Goddard on space weather and space physics, Jim is on our council, but several of us had a chance to go over and actually visit him and his colleagues and what they do at NASA Goddard, and I've never seen anybody so excited about their work and what they do. So you're in for a treat, and I'm going to get off the stage and let him talk because he's really got some really important things to talk to us about. So he is a research astrophysicist. Is that
That's
correct?
the official title, yeah.
That's his official title at NASA Goddard. He studies heliophysics, space weather, and you're going to learn what space weather really means and how exciting it is, and probably some other things that you're going to talk to us about, right, Jim? So thanks for being here.
My pleasure.
Let's get started.
Okay, thanks. Thank you very much. It's a treat to be here, and it was a treat to have you guys visit because, indeed, I am very enthusiastic. I'm a lucky son of a gun to actually get paid to do what I do. But you guys were very enthusiastic as well. You really were, I think, appreciative of learning about the science, and so that kind of fed onto my excitement. So thanks for that nice visit. Okay, the title of my talk here is Heliophysics and the Weather in Space. But a subtitle is The Science and Societal Relevance of AGU's Space Physics and Astronomy section. You probably know that we have this section, the SPA section, but I'm guessing a lot of you don't really know that much about what it's really all about. What kind of science does it deal with? So what I'd like to do is give you a better understanding of what we do in the SPA section, and also an appreciation for how SPA science benefits society. As you know, the AGU is making a big push to address societal relevance. How can our science help mankind? And I think SPA science has a lot to offer in this regard, so hopefully you'll come to appreciate that a little bit better. Now, I've actually never given a talk before of this type. I've had you visit, and it was just kind of an informal chat, but this is a formal presentation of a type I haven't given before. Furthermore, I've been apologizing a bit already this morning. All hell sort of broke loose at work this week, so I didn't have as much time to work on this talk as I would have liked, so it's a little bit rough around the edges. But maybe that's okay, because I'm hoping this is not so much a formal lecture, but more of a discussion. So please, feel free to interrupt me at any time, ask a question. If not very clear in explaining something, then give me a chance to try again, and let's try to do it that way. Great. So I have to give some special thanks here to two people. Michael Hesse, who's the director of the NASA Space Weather Lab, that's based at Goddard, and Chris met Michael when she was visiting. And then Tom Bogdan, director of NOAA's Space Weather Prediction Center. Some of the graphics I'll be showing, especially sort of the space weather-related graphics I got from these guys. Okay, so maybe as a start, I should kind of define what space physics and astronomy is. Okay? And really, that term is kind of old-fashioned. Nowadays, we talk about the discipline of heliophysics. So heliophysics and space weather astronomy are kind of the same thing. So this field deals with really four different physical regimes. They're indicated here. So first of all, we have the sun at the center of the solar system. The space between the sun and the Earth, and indeed between the sun and all of the planets, is called the heliosphere. Closer to the Earth, and this is not at all to scale, by the way. I mean, the Earth is tiny compared to the sun. And, you thought it was hot last week. Wow. The outermost atmosphere of the Earth is called the magnetosphere, and it is controlled by the Earth's magnetic field. Now, this is just an artist's conception of that field. It doesn't really look that way. I mean, the field is an invisible force field. We see it because gas is aligned with the field. But this is just an artist's conception. And then at the base here is a fairly thin layer called the ionosphere. It starts, well, fairly high up, actually, maybe at 50 kilometers or so, and then goes up to perhaps 2,000 kilometers from the surface of the Earth. So it's far above where we operate. We operate in the troposphere, and this is well above the troposphere. But still, on the big scheme of things, it's a very thin layer. Okay, so these are the four regimes. I'll talk mostly about the sun, actually. That's my specialty. I'm a solar physicist. So I hope that's okay with you, but that's my plan here. All right, so to start out, I would point out to you that the sun looks very different depending upon the wavelength of light in which you observe it. And this wavelength tends to be related to the temperature of the gas that's emitting the radiation. So here we have 4 examples. This is the sun as seen in visible light. This is maybe what you're most accustomed to. And the spectrum of light is very, very broad. Our eyes are sensitive to the visible part, but that's a really thin slice within the broad spectrum. As we go to shorter wavelengths, which means higher energies, we go into the ultraviolet, and then the X-ray, and finally the gamma ray. And as we go to longer wavelengths from visible, that corresponds to lower energy. There's the infrared, the microwave, and the radio. But in the visible, the part that our eyes are sensitive to, this is what the sun looks like. Fairly bland, really. There are a few of these little sunspots here, dark regions. But then as we go to ultraviolet wavelengths, as shown here and here, we're going higher up in temperature. The gas that's emitting this radiation is hotter. In this case, about 20,000 degrees. Oh, the photosphere is 6,000 degrees. That's actually very cold by solar standards. Seems hot, but that's cold. The solar surface, which we call the photosphere, is cold. Then we move up in the atmosphere to 20,000 degrees, 800,000 degrees. And finally, as we look at the sun in X-rays, we get up to gases that are about 2 million degrees, and sometimes higher. And so there's quite a difference in the appearance of the sun in these different wavelengths. So again, here is the cold photosphere. This outer part is called the corona. And I'll be mostly talking about the corona and the photosphere. So the photosphere is the cold surface. The corona is the hot gas above the surface. And let me say something about surface. Some people, I think, are confused. We talk about the surface of the sun as though it's a solid body. I mean, it's not like that at all. The entire sun is a gas. But we call it the surface because the properties of this gas change very abruptly as you go from the photosphere up into the corona. Cold, dense photosphere, go up a very short distance and you get to a very hot, very tenuous or thin gas, which is the corona. So it's a very abrupt transition. And that gives us the sense that there is a sharp surface, but there really isn't. So it's really much like clouds, a cumulus cloud. You look at these puffy clouds, sometimes they seem to have a very sharp edge. Well, it's not as though the cloud is solid. It's just a sharp transition from the gas in the cloud, which is very moist, has all the suspended water particles, and then outside the cloud, the air is dry. And because that transition is sharp, it looks like you have a hard surface, but you don't. It's exactly the same thing with the sun. Okay, so now let's go into a little bit of basic physics, just for a short while. Talking about temperature, I've been referring to gases, the solar gases. Really, the solar gas is a special type of gas called a plasma. So in a gas, it's made up of various particles. Like in this room, we have oxygen and nitrogen and helium and hydrogen. And these particles are bouncing around, crashing off each other. If we increase the temperature of the gas, they move more quickly and have more violent collisions. And if we increase the temperature still further, eventually we get to a point where the electrons are stripped off of the atoms. An atom, thinking back to high school, an atom has a nucleus made of positively charged protons, and then orbiting those are negatively charged electrons. And there are just as many electrons as protons, so the net charge is 0. So we call the atoms neutral. Okay? But if we have really high temperatures and these things are crashing into each other and really violently, we can knock off one or more electrons. So in that case, the atom has a net positive charge. It's lost some electrons. And then we call it an ion, actually. It's only an atom if it's neutral. Then the term changes, and it's called an ion. And also, we have these free electrons zipping around, not attached to any atom. So it's a soup of charged particles, positive ions and negative electrons, and that is a plasma. And 99% of the universe is a plasma, in fact. It's the most common form of matter. Okay, the neat thing about plasmas is that they interact very strongly with magnetic fields. That's not true of neutral gases. So in this room, right, we have a neutral gas. There are magnetic fields throughout the room. It's the Earth's magnetic field, the same field that causes the needle on a magnet, on a compass rather, to point north always. But the gas and the magnetic field don't really care about each other. If I had a magnet, I could wave it around, and the gas in the room wouldn't even know that was the case. But if we have a plasma, it's a much different story. There's a very strong interaction between the plasma and the magnetic field. And that happens by way of electrical currents. Okay, we have these electrons in the plasma, like I mentioned, and they can move around and cause currents. Just like electrons in a wire, in these cables, we have electrons flowing through the plasma and giving rise to currents. Currents generate magnetic fields, and magnetic fields in turn influence the current. So it's a very close interaction of the two. And one consequence is that the plasma and magnetic field tend to be frozen together. So the plasma cannot move unless the magnetic field moves, and vice versa. And that gives rise to some very, very interesting phenomena. That's what I'll be talking about. Okay, so let's see. I wanted to cover a few points. You're probably thinking, oh my gosh, is this going to go on for an hour, this basic physics lecture? No, it will not be the case. But those are just some kind of basic points that I hope will help you to better appreciate the data which I'll be showing. All right. So now, here is the corona seen in X-rays. This is a montage. It's one picture taken every year for the 11 years of the solar cycle. So the sun evolves on many different time scales. First of all, the sun rotates with a 27-day period. So even if it didn't change, those features you would see rotating across the face of the sun. So it would seem to change. But those features change themselves. They evolve in time, again with many different time scales. And one of the time scales is the 11-year solar cycle. The sun's overall level of activity waxes and wanes with this 11-year period. So here where you see a lot of bright X-ray emission, that's the maximum of the solar cycle. And then as the years pass, you go by and into the minimum of the solar cycle, and then you ramp up again to the next maximum. All right. Now let's talk about some of these features we see. These bright patches here are called solar active regions. It's where the magnetic field is very strong, the gas is especially hot, and in fact it's relatively dense. It's not dense compared to that photosphere, but just up in the corona, it's dense compared to other parts of the corona. And this is where a lot of interesting things happen, like solar flares and coronal mass ejections and other eruptions. We'll talk about that. But then you have dark areas, especially at the north and south poles, here, up here, here, and sometimes extending down toward the equator, like here. Those are called coronal holes. That's where the gas is relatively cool. It's still hot. It's coronal, so it's a million degree-ish, but it's not several million like in the active region. So it's relatively cool for the corona. It's relatively dense, and that's where the solar wind comes from. Oh yeah, I wanted to make a point back here that I didn't. So the sun emits constantly this magnetized plasma blowing outward to produce what we call the solar wind. It spews this out and it permeates all of the heliosphere. And that solar wind causes the Earth's magnetic field in the magnetosphere to sort of be draped backward. You have this wind blowing at it. So it creates this shape here which would otherwise be fairly symmetric. Instead, because the wind is blowing out, you get kind of a blunt nose here, and then in the tail it's stretched way, way back. That's from the wind blowing by. But normally the wind doesn't interact with the magnetic field of the Earth, except for kind of changing its shape. But sometimes it does. Sometimes there is a very close interaction between the solar wind magnetic field and the Earth's magnetic field, especially here at this area we call the nose. And there's actually a breaking of the field and a reconnection and exchange of parts. And it's kind of complex, but this is what gives rise to many interesting things. So the solar wind, which distorts the magnetosphere, comes from these dark coronal holes. Okay. Here are the same times of the sun, one per year, but showing instead of the X-ray corona, this is the surface, or the photosphere, and this is a map of magnetic fields at the surface. So white areas are strong positive magnetic field, dark areas are strong negative. Remember, magnetic fields have polarity, the two poles of a magnet, positive and negative. It's the same thing. Then gray areas are where the field is weaker. But you see that the amount of magnetism on the sun changes during the solar cycle. And it's related to the changes in activity. A lot of magnetic fields during the solar maximum, not so many during the minimum. And let me toggle back and forth, and you can see the relationship there. The active regions tend to be where there are the strongest magnetic fields. Okay, So let me really drive home this point about magnetic fields being important. And this is really the thing I want you to take away most, or one of the things I want you to take away most, are these 2 points. The gas throughout the heliosphere, in the sun, in the magnetosphere, is so hot that the particles are not neutral. So we have this magnetically charged plasma, and the plasma interacts with the magnetic field, and virtually everything interesting that goes on in heliophysics is related to that. So to emphasize this even further, let me start out by showing here, this is just an image of iron filings with a bar magnet nearby. You've all seen this before, I'm sure. And these are what the magnetic lines of force look like as produced by this bar magnet. Okay, now let's take a look at the sun. Here is a close-up of one of those solar active regions. And hopefully you can see these very clear patterns that really resemble the patterns of iron filings in the bar magnet. So just as the magnetic field of the bar magnet controls the iron filings, the magnetic field of the corona controls the hot solar plasma. And here's another example. This is an image of the sun during a total solar eclipse. So that's where you have the moon here blocking out the super bright face of the sun, revealing the much fainter corona. And there are lots of little patterns here which match the patterns in the magnetic fields from this model here. We measure the fields in the photosphere very well. I showed you an example of that. We cannot measure the fields in the corona very well, unfortunately. We try, but it's a very difficult thing to do. So instead, we take the measured fields at the solar surface and we apply physical models to infer what the field is like up in the corona. So this shows the magnetic field lines from one of these physical models, based on observations of the photospheric field, and you see that there's a strong resemblance here. So the whole point is, we're certain that magnetic fields are important, and as I put it here, magnetic fields rule the corona. Okay. So now let's ask the question, what happens when the magnetic field breaks? Okay. Magnetic fields are in many ways like invisible rubber bands. They have tension in them. And they can be stretched or twisted or distorted. And if those stresses become too great, the rubber bands break and release energy, and the magnetic fields break and release energy. Just think of it. You're twisting a rubber band, twist and twist and twist, and stretching it, and eventually snap, there it goes. Same thing happens with magnetic fields. So when we have small breaks in the magnetic field, then that's what heats the corona to its temperature of 1,000,000 degrees or more. Just lots of little small breaks everywhere. But sometimes there's a huge break, like the magnetic field of an entire active region will break on a large scale, and that'll produce these much more violent things like solar flares and coronal mass ejections. And for shorthand, we oftentimes call coronal mass ejections CMEs. Okay. So now let's talk for a moment about this issue of how the corona gets hot. As I say, it involves the breaking of the magnetic field on a small scale. This coronal heating problem, it's been one of the fundamental problems in all of astrophysics for many, many years, for decades literally. We have a basic idea of what's going on, this breaking of the magnetic field, but the details of that we're still trying to work out. Okay, so this is a problem that's near and dear to my heart. And this is basically what we think is going on. This is a movie of the solar photosphere, the solar surface. And there happens to be a gigantic sunspot here, but really I want you to concentrate on these areas here. And you see that there's a lot of motion, a lot of turbulence going on. It's very much like what happens if you have a pot of oil on the stove. And when it gets hot, you see this pattern developing, this sort of roiling pattern. The hot oil rises to the surface, it cools off and falls back down. The very same thing is happening at the solar surface. So these turbulent motions at the solar surface stir the coronal magnetic field. Because the field, these rubber bands if you will, are stuck in the surface. They extend up into the corona, but they're stuck in the surface. So the surface is moving around in a random way, and it's taking the ends of those rubber bands, and it's really mixing things up, stirring up the coronal field, causing it to become tangled. So indeed, the stirring at the surface causes the field to become tangled and stressed. And when that field breaks, because it is stressed, we have these small bursts of energy that I referred to, and we call them nanoflares. They're miniature versions of large flares. And these nanoflares heat the gas to 1,000,000 degrees. And millions of these nanoflares are occurring every second across the sun. So So they're very small, but very, very numerous. And this is, here's our active region again. We zoom in on this location here. We believe the magnetic field lines look like this, kind of tangled up. And it turns out that that means there are sheets of electric current there as well. And that's where a lot of these nanoflares occur. OK, so that's coronal heating. Let me now show you a movie. It's a format that I wasn't able to put into PowerPoint. Where is it? This is it. So here is an active region coming around the limb of the sun, the edge we call the limb. These are observations made in the ultraviolet by our new mission called the Solar Dynamics Observatory, SDO. It was launched a bit over a year ago. It's producing incredible data. So here you see all this activity, these little nanoflares going off. These are not huge eruptions. These are just very small-scale things. And you see the loops of plasma produced by the magnetic fields, just like the bar magnet does. So we're trying to understand the details of just how all this takes place. All right, so back to PowerPoint. OK. Now let's move away from the small breaks in the field to these very large breaks that give us big eruptions. Here are a couple of examples. These are prominences that are erupting. Prominences, this particular emission is from that sort of 80,000 degree gas that I showed in the early slide. It happens to be called the chromosphere. That's another thin layer. But sometimes we have gas at that temperature sitting up in the corona, which is normally much hotter. So these are special features called solar prominences, and they frequently erupt. And let's see how that goes. Again, these are data from the SDO mission that I mentioned. So I think this is pretty cool, man. I really get turned on by this. And it's so complicated. If you
really hate your job.
I hate my job. But I love this and I hate it. I love it because it's so cool. But I hate it because the complexity is so great. We're trying to conceptualize what the magnetic field is doing. And we know the properties of magnetic fields. We know they obey certain equations. And it's so dang hard to understand how it all fits together in these types of eruptions. But here's another example. And these typically are associated with solar flares. That's a term that probably most of you know. And also these coronal mass ejections, CMEs. As I say here, these are all interrelated phenomena: prominence eruptions, CMEs, and flares. OK. Now let's talk about CMEs, coronal mass ejections. Here are examples of 3 CMEs. Now, the CMEs are best observed with instruments called coronagraphs. These are telescopes that create artificial eclipses. So just like the moon blocked out the bright face of the sun in the eclipse image I showed before, allowing us to see the much fainter corona, these telescopes do that as well. But they don't do that as well as the moon for various reasons that relate to sophisticated optics and scattered light and this and that. So instead of making a disk to block the face of the sun that's just the size of the disk of the sun, which the moon is, which is really pretty amazing actually. It's coincidence that the moon happens to be just the right size to just block out the face of the sun and not a whole lot more. So we do this with an instrument. This is here, this blocking feature. It's called the occulting disk. And this is the stick that holds it in place in front of the lens of the telescope. And this white circle here would correspond to the rim of the sun, the photosphere. And in this case, we've actually taken an image of the sun in the ultraviolet and put it in there at the proper scale. So these were taken with different coronagraphs. That's why the relative sizes of the disks in the sun are different. But as you can see, these are enormous explosions. I mean, huge parts of the corona are blown outward very, very rapidly. So it's 1 billion tons of matter shot out from the sun at 1 million miles per hour. These are the largest explosions in the solar system by far. Just huge, huge, huge events. This one's kind of neat because these dots here, these are planets. And the lines are artifacts. But then you can see, I think, some of the stars in the background as well. So here are still images of coronal mass ejections. Let me show you a movie. Here's one shooting off. This is taken with a mission, a relatively new mission as well, called STEREO. And STEREO actually consists of 2 spacecraft that were launched at the same time. They're not orbiting the Earth. You know, most of our missions that observe the Sun orbit the Earth. These are orbiting the Sun with the Earth. One is drifting ahead of the Earth, and one is lagging behind. So it's been several years now, and they've drifted apart, so that now they are basically on the sides of the Sun. One is on the right side of the Sun, and one is on the left side of the Sun. And this particular movie came from one of those STEREO spacecraft. Okay, here is a sequence. It lasts a month. This is from back in 1997, from a different mission. It was a joint project between NASA and ESA, the European Space Agency, called SOHO, the Solar and Heliospheric Observatory. And I show this even though it's old because this was back when the Sun was in an active part of the solar cycle. So these CMEs were occurring much more frequently. You know, lately they haven't been occurring frequently at all. But here you go, and here's the star field moving past the Sun. CMEs are going off. I think at one point you see a planet as a planet. I don't remember which one, Mercury perhaps. There was a comet that went by. So generally you see these things kind of flying out to the side. But sometimes, just a moment ago, you see a big ring growing in the field of view. Let's wait and see that again. That corresponds to CMEs that are directed right at us. And they appear as these halos. I think it's coming up, I believe. Look for a ring growing very rapidly, centered on the Sun. There it is, right there. That's a CME being shot right out at the Earth. Okay, now here is an artist's conception of the sequences that follow. Ooh. So here's the Sun. We're zooming around the Sun. There goes a coronal mass ejection. Flying through the heliosphere, gets to the Earth's magnetosphere. Here's the interaction I told you about where the magnetic fields actually exchange parts. And something else happens back here. And you end up ultimately producing the aurora, the northern and southern lights. So, very dramatic, very dramatic. And we understand a lot of this. I mean, it's an artist's conception, but this artist has obviously spoken to scientists, and we know the details of what's going on in all these different phases. Okay, to prove that point to you, I want to show you a numerical model. This is a gigantic numerical model run on a huge computer, supercomputer. It's going to show a coronal mass ejection lifting off from the Sun, propagating through the heliosphere, and eventually interacting with the Earth's magnetosphere. These lines here are the magnetic lines of force, and the colors are the density of the plasma. All right, so here we go. So there's the Sun. This is all to scale now. This is completely realistic. There goes the CME, away from the Sun. Now we're going to pan outward in a moment. And there it is. The Sun's very small here. There's the giant CME going through the heliosphere, headed toward the Earth. Now, believe it or not, the Earth is in here somewhere. These lines show the numerical grid. And it has big grid cells and small grid cells. Okay. There it is. There's the Earth. That gives you a sense of scale. And there's the magnetosphere. Now, the CME is going to crash into it. The magnetic fields are going to interact here. And that leads to an interaction of magnetic fields back here, which ultimately produce the aurora borealis and australis, the northern and southern lights. So very sophisticated numerical models. The discipline that is used, if you will, to study these things is called magnetohydrodynamics. Magneto because of the magnetic field, hydro that refers to the plasma, to the fluid. So MHD, magnetohydrodynamics. Okay, so a number of consequences. One is, as I mentioned, the aurorae. So here are some northern light images from very recently, less than a week ago, August 5, August 6, August 6 again. There was a big flare in a big CME that was directed toward the Earth, and it produced these northern lights. So up in British Columbia, it's spectacular. That's not a surprise because, well, I should say we see these northern lights best at the very high latitudes, because that's where the magnetic fields that are involved with this map down to the solar surface. We have these magnetic reconnections far out in the magnetosphere, and those field lines then map down to the solar surface up in the polar regions. And so the reconnection produces energetic particles that stream along those field lines and collide with the atoms in the atmosphere and cause them to glow. So that's why it's up in the north. But for really big events, we can see northern lights even down at lower latitudes. This one is from Michigan, and this one from Utah, very low latitude. So this was a major event. Okay, back to a couple movies now. Not that one. Not that one. Yeah, that's for the end. That's not the one I wanted to show. Okay. So this is, again, from just less than a week ago, a movie up in Northwest Territories in Canada. Pretty spectacular, isn't it? Yeah, I'd love to be camping out there for a couple days. Somebody is, right? Who did I speak with who's going to Alaska? You're going to Alaska just soon, so hopefully you'll see a lot of these northern lights there. Okay. So now, this is what the aurora looks like from a spacecraft orbiting the Earth at very high altitude. It's called the polar spacecraft. This is just a cartoon of the Earth, but those, the glowing there, that's real data observed from the spacecraft, northern lights. Do it one more time. Okay, so that's the tease. Now you'll stick around, otherwise you might have walked out, but if you think there's going to be a daily show at the end. Okay, so now let's finally get to space weather. What are the consequences of all these phenomena? Well, some consequences are very nice. I mean, we get the northern lights. That's really great. But there are a lot of nasty things that happen as well. So first of all, the sources of space weather. We've already basically gone over this. We have X-ray and UV radiation from solar flares. And these are photons. This is light. These are not particles, but this is light. Then also we do have energetic particles, both electrons and protons, produced by very large flares and also by very fast coronal mass ejections. So Chris knows about this, actually. Chris, this gal is really sharp. We're lucky to have her in charge here because she's such a quick learner. So I'm talking about some of these things and going pretty quickly and figuring out this is just flying over her head, but she's on top of it. So if a coronal mass ejection is fast enough, it creates a shock. There's the solar wind blowing out, typically at, say, 300-400 kilometers per second. And to get a shock, you have to be traveling very fast compared to the medium that you're traveling in. So the CME has to be much faster than 300 or 400 kilometers per second. It needs to typically be above, let's say, 1,000 kilometers per second. And if it is, it creates a shock. And shocks are very good at accelerating particles to extremely high energies. We talked about the plasma and the gas having the particles bouncing around, and they all bounce around at more or less the same speed. But sometimes you can take some of those particles and accelerate them to far, far, far higher speeds, and that's what happens in shocks. So these particles are traveling nearly at the speed of light. They're called relativistic. So we can get that. And then finally, once the CME reaches the magnetosphere, that takes typically 2 days to go from the sun to the magnetosphere, then it causes a geomagnetic storm. And these are some of the systems and activities that are impacted by these events. Communications is affected. You can have disruption or total blackouts in communication. GPS is strongly affected. And GPS is used nowadays for so many things. For navigation, for agriculture. I mean, farmers use GPS to plow their fields, to plow straight lines and make, I guess, the optimum use of the land they have. GPS is used for surveying, for guidance of precision weapons. We have these incredible missiles and things nowadays, that many of which rely on GPS to hit their target accurately. And there are many, many other examples where GPS comes in. These sorts of things, especially the geomagnetic storms, affect electrical power grids, can cause blackouts in grids. Command and control of satellites is affected. Airlines are affected, and Chris also knows about this, because if we get one of these fast CMEs that accelerates high-energy particles, those particles, and also the photons coming from flares, can disrupt communications up at high latitudes. And I'll say a little bit more about that later. But there are also GPS effects as well. Astronaut activities are affected. You can't go on spacewalks when you have these high-energy particles flying around. It's very, very dangerous. So there are astronaut activities at NASA and other space agencies. But now we're getting into commercial space flight, right? There are these private companies that are building spaceships that ultimately will take tourists up into space. So space weather will be a big deal for them. Banking and finance systems are affected. And even things like oil pipeline corrosion. If we have a large geomagnetic storm, it generates currents in these long pipes, and that causes corrosion to increase at a very rapid rate. And it's a big deal, it turns out. OK, so let me give 2 or 3 or 4 specific examples. I'll go through this fairly quickly. There was a huge event in March of 1989. I was listening to the radio on the way in, listening to NPR. And this is the 50th anniversary of the building of the Berlin Wall. And the Berlin Wall came down in 1989. So I got to thinking, maybe space weather did it. But that's a little bit speculative. Something which is not speculative is that it caused a massive power blackout. The company Hydro-Quebec went down. The entire grid went down. It's this yellow region here, I believe. For 9 hours, people didn't have power. Transformers got fried. Here's an example. And power systems were affected all throughout North America. There was tripping of these systems, which, well, it means various things. But anyways, there were a multitude of effects, but especially in Quebec, power going out for 9 hours, affecting millions of people. That's a big deal. Other examples include the disabling of communications satellites. In 1994, there were 2 satellites called Enoch E2 that went out, basically, because of a geomagnetic event. One satellite was recovered in a few hours. The other satellite took 6 months to recover. And the company estimated that the total losses from that were about $70 million. Another somewhat more recent example from 2003, this satellite here, a Japanese satellite, communication satellite, was completely lost, never to be recovered again. And that satellite cost $570 million. There's this rerouting of polar airline flights that I mentioned. The pilots communicate with high-frequency radio communication, HF communication. And when we have one of these solar storms, that communication can go down, disruption or complete blackout. Now, at lower latitudes, below 82 degrees, there's a backup. We can use satellites, communication satellites, as a backup. But those satellites cannot send a signal to the poles. Anything above 82 degrees is over the horizon, so to speak, for these satellites. So if that's the case, since there's no backup, if the airlines know there's going to be a communication blackout, they can't fly there. It's just too dangerous. There are FAA regulations. And nowadays, many, many flights go over the poles. Here are examples of routes. Whenever you go to Asia or some parts of Europe, you're flying over the North Pole or very close to it. And so 82 degrees is sort of this whole region here. So all of these routes would be affected. And in fact, last year, there were 800 flights that had to be changed because of that. It's changed in some way. So that results in delays. There are added fuel costs because you have to fly around the pole, fly a greater distance. It requires the airlines to have smaller passenger loads. So it's an inconvenience, and it's a real cost. OK, so what about the possibility of a superstorm in the future, a really huge storm? Not one that's just crazy, wild, unrealistic, but one of the magnitude that, in fact, occurred back in 1869. It's called the Carrington event, named after this guy Carrington. It didn't have that big consequences back then because we didn't have these sophisticated technologies. So there wasn't much really for the storm to do. It did cause the telegraph operator wires, not the wires, but the needles, I guess, to bounce around crazy. That's an impact, not a huge one. But now, because we rely so much more on advanced technologies, especially space-based technologies, we're far more susceptible. So what if we had a storm of this size? Well, there was a study published recently by the National Academy of Sciences that concluded that potentially, in a worst-case scenario, but one that's not far-fetched, the consequences could be incredible. Billions of dollars in damages, and in fact, millions of deaths. Millions of people across the globe could die. So how would that happen? Well, if the power grids go down and if the transformers get blown out, then we have no way of generating power or transmitting power for a long period of time. You know, we have to build new transformers. Apparently that takes a long time, at least 6 months. But it might take even longer because how do you build them if you don't have the power to run all the machines and everything that you need to build them? So they've gone through and in a plausible way looked at the chain of events and concluded that in a worst case, it could be absolutely catastrophic. Something to think about. All right. So for these reasons, we've gotten into the business of space weather forecasting. And if we can forecast these events in advance, obviously that's what forecast means, then we can undertake some strategies to mitigate the consequences. Just as some examples here, we can delay critical operations, both military and civilian operations. You know, if we're going to rely on radio signals and we think that those radio signals are going to get disrupted, then let's not undertake those activities. Let's wait until a safer time. Satellites can be put in a special mode called a safe mode, so they're less susceptible to being damaged. Power grids can be operated a little bit differently. I mean, right now, grids have all of these switches. I mean, the power grid is really interconnected. There are different companies, but everything is all interconnected, and one company buys power from another, and you know, it's very much that way. It's like the internet, all interconnected. And these grids have switches, so if the voltage gets higher than it should be, the switch flips, and the power is shunted to a different part of the grid. Now, if you have a big storm, you get the shunting from one region to another, but that section of the grid is stressed as well, so its switch flips, and it shunts it to another section, and very quickly you have all the power going to like one little place, and that can't happen, so the whole grid goes down. But if you suspect there's going to be a storm, you can increase the tolerance in these switches. I mean, right now they have them set at very conservative levels, but you can set them a little higher so that this kind of a cascading effect doesn't happen. And then with airlines, we've already talked about that. You can either delay or reroute the flights. And these are just some of the examples. There are many, many more. So we understand the importance of space weather. And now we have space weather forecast service providers. There's the NOAA Space Weather Prediction Center and NASA's Space Weather Lab. I mentioned the directors of those labs that gave me some of these materials. There's also the Air Force Weather Agency. Here are some of the products that they provide, and they have many, many customers. You can look at their list of customers. You know, all kinds of government agencies and private companies, you know, utilities companies, airlines, many, many customers. Even oil companies. It turns out oil companies rely on GPS for their drilling, and so if GPS is inaccurate, it causes big problems. So this is one of the web pages from the SWPC, Space Weather Prediction Center at NOAA, showing some of the products that they have. Here's another example from NASA's Space Weather Lab. And Chris saw some very similar things when you were visiting. Recall I showed you a number of aurora photographs from a few days ago, produced by a CME. Well, when that CME went off, we measured its properties with a coronagraph and with other instruments. And then we tried to infer, well, what's it going to do when it hits the Earth? We do that with these MHD models, much like the one that I showed you. So here are the results of one of those models. This is looking down on the sun, down in the solar system from above, from way up in the North Pole, you can imagine. So here's the sun. One of these is the Earth. Which is the Earth? The Earth is round. This is the Earth right here. This is showing in colors the density of the solar wind. And there's the CME going off in this model. And so we can predict then what are the conditions going to be like when it hits the Earth. And we need to know things like how fast will it be traveling? What will the orientation of the magnetic field be? Because the degree to which the CME interacts with the magnetosphere depends upon the orientation of the field. So all these complexities are worked out in these models, and then predictions are made. Oh, and this is a view looking from the side, looking along the plane of the solar system, if you will. And then you can predict things like the fluxes of energetic particles, that's shown here. And the CME did, in fact, produce huge increases in high-energy protons. OK? Now, getting near the end here, we'll have that Daily Show clip soon, but I want to make one final comment. So space weather forecasting is absolutely in its infancy. We're just starting out. Some people estimate that space weather forecasting is where tropospheric weather forecasting, you know, the forecasting you see on the news, how it was 40 or 50 years ago. We're just starting out. But to get much better at our forecasting, we have to have a good physical understanding of how space weather works. We have to be able to build these sophisticated models that are based on realistic physics. So we need the physical understanding necessary to build realistic numerical models, and that is the science of the SPA. So that's why we're important. That's why we're so appreciative that you guys are helping us to advance the science. Any questions at all? Please. Yeah. Oh, you're welcome.
The coronal mass ejections hit the Earth's magnetic sphere.
Mm-hmm.
Presumably they don't stop there. Where do they go on to?
For the most part, like the solar wind, it kind of slides around the magnetosphere. Although if there is this interaction, this exchanging of magnetic fields, then it's a different situation. But these things are huge. You saw in that one model, the Earth is so teeny tiny in comparison. So they keep going on through the solar system. And they affect other planets as well. So now as we talk about traveling to other planets, you know, maybe having a base on Mars eventually, we have to worry about these things. And especially since other planets don't necessarily have strong magnetic fields. So the effects of space weather are much more severe. You know, our magnetosphere, for the most part, shields us from all these particles. But it's not the case elsewhere. Yeah.
So is the sun shrinking if it's losing so much mass?
That's a good question. You're thinking. That's very good. No, it turns out the amount of mass it's losing is absolutely insignificant. Because the sun is, for the most part, held together with gravity. I mean, it doesn't just fly apart. Gravity self-gravity is pulling everything tighter and tighter. And so the densities at the core of the sun are fantastically large. There's so much more mass contained in the core than there is in all of the solar wind.
What if we had one of these extreme CME events? Could it break our magnetic field or rupture it or flip it or something?
Well, it wouldn't flip it. The kinds of things that were shown in that graphic and in the numerical model would be exaggerated. So you get this linking of the magnetic field in the CME with the magnetic field of the Earth, and that generates currents and various other things. It gets very complicated. But the Earth's magnetic field would still be there, and it would recover. But here's something interesting. Just as the sun's magnetic field goes through an 11-year solar cycle, the Earth's magnetic field has a solar cycle as well. It's much longer time scale. I don't remember. I think the period is 100,000 years or something like that. And it's not quite as regular. But people are kind of wondering, what happens when the Earth's magnetic field reverses? So in the solar cycle, not only does the magnetic field get stronger and weaker, but the polarity changes. The North Pole changes from positive polarity to negative. And during that transition time, the strength of the field is weaker, and the shape of the field, let me put it that way, is weaker as well. So we'll have much less shielding than we have right now. So people have wondered about that. What happens when the Earth's field flips? You know, it could be that space weather will be far, far, far worse. But you know, it's like tens of or hundreds of thousands of years off, so don't be too worried about it. So this gentleman's had his hand up for a long time.
Oh, yeah. So what is the substorm?
Substorm, very good. In the first cartoon that I showed, I guess the same one that John Stewart showed, first the CME hit the front side of the magnetosphere and caused the field lines to to reconnect the CME field line with the Earth's field line. And then those field lines got swept back to the tail of the magnetosphere. Okay? And that happens, in fact, that basic process a lot, just with the solar wind. Whenever the solar wind's magnetic field is pointed in a southward direction, this happens just very gradually and slowly. But that means that the amount of magnetic field in the tail is building up and getting bigger and bigger and bigger. And eventually, in the middle of the tail, if you will, the magnetic fields are pointed out on one side, just to the north, and in to the other side, to the south. And oppositely directed magnetic fields like to reconnect. So the fields of the magnetosphere reconnect with themselves, and you produce a loop which then pulls in closer to the Earth and gives rise to the substorm. So that's a substorm. That doesn't require a CME.
So in Neptune terms, after one of these huge CME events, what's the travel time to when we feel it on Earth?
Yeah, the travel time of the CME, if it's a fast one that produces these big effects, it's roughly a couple days, 1 to 2 days. So if we see a CME go off, we can analyze it and make predictions about what the consequences might be. So that's great, but CMEs are also associated with flares. And flares produce these bursts of X-rays. And those X-rays take 8 minutes to get to the Earth. So there's no way, once you see a flare go off, there's no way of taking action to prepare for it. So you have to predict the flare and the CME before they occur. And we're actively pursuing that. I mean, I've been involved with doing some of that, the theory of the initiation of flares and CMEs. So for that burst of photons, X-rays, which do affect communications and other things, there's no warning once it happens, really. There's no way to react. With the geomagnetic storm from the CME, that takes 2 days, so there is plenty of time to react. But as the CME is traveling, if it's traveling quickly enough to produce a shock, like we discussed, the shock accelerates these particles, and the particles move almost as fast as light. So they may take just a few tens of minutes to get to the Earth. So if you have a CME that goes off and very quickly it forms a shock, you're going to get a dose of these high energy particles within minutes, and there's probably not enough time to respond to that. So once again, to prepare for that kind of a thing, you really would like to predict the CME before it occurs.
I'm not sure if I understood correctly, but are photons essentially light particles?
Exactly right, yeah.
So how do these light particles affect communications?
Yeah, what happens is both with the photon light particles and also with the real matter particles, electrons and protons, they get into the atmosphere. And they get in with the real particles, since they're guided by the magnetic field, they get into the atmosphere mostly up at the very high latitudes, because that's where the field has the right connections, if you will. Photons don't care about the magnetic field. They just bathe the entire Earth. So what they do is they're absorbed by the Earth's upper atmosphere, by the ionosphere. And there are a couple of things that happen. For one, the ionosphere heats up. So it heats up and it expands. Right? So say you're at a given altitude, you're some satellite which is orbiting at a given altitude. Before the flare, you experience a certain density, and that's giving you some drag. But now when the atmosphere heats up and swells, now the density at your altitude is much higher, so you experience much bigger drag. So what happens is we lose track temporarily of all of our space assets, it's called, all of our satellites, and also, equally importantly, the space debris. There's a lot of junk in space, and we track all that. We need to know where it is so that we can move our spacecraft to avoid colliding with debris. And so when these orbits are affected by the swelling of the atmosphere, we lose track of everything, and it's a dicey time. In addition, though, the atmosphere it becomes heated and it swells, but it becomes more ionized. So these photons can hit one of our neutral atoms and knock off an electron, just like what happens when the atoms are crashing into each other. So then the atmosphere is ionized, and we rely on the ionization state of the atmosphere for a lot of our communications, because radio signals are affected by this plasma. And we need to know the properties of the plasma to know exactly how we're bouncing signals off the ionosphere. And if the properties change, the signal may go farther than we thought it would, or not as far. And then there's finally an effect called scintillation, where you have all this sort of turbulence in the atmosphere, and that just makes the paths of the radio signals not bounce in straight lines, but kind of wander all over the place.
How long do disruptions typically last, and are they related to the force of the team?
They typically last, it depends upon the effect that you're talking about, but these geomagnetic storms can last for a couple of days. Remember, I showed those photos of the recent aurora, and they span 2 days. So what happens is in the storm, you get very immediate effects, but then other things happen that take longer to decay away. You've heard maybe of the radiation belts, the Van Allen radiation belts. That's high up in our atmosphere. There are charged particles orbiting around. Well, those belts get energized. More particles get into them, and that causes various currents, and that affects all of our systems. And then gradually those excess currents dissipate, but it can take several days.
What is the origin of Sun's magnetic field, and do you know anything about magnetic fields of other stars?
Yeah, we do, quite a lot actually. We can measure the magnetic fields of other stars. We can measure nowadays star spots. Not so much by imaging the star, but through complex techniques involving spectroscopy, we can infer how big the star spots are and how strong they are. And it turns out for many stars, instead of having small sunspots at lower latitudes, you tend to get these gigantic sunspots near the poles that cover a big part of the pole. Okay, so how are they formed? Well, there was a primordial magnetic field in the nebula which collapsed to form the solar system and the planets and the sun and all that. And as long as you have some finite magnetic field, in a plasma, it can be amplified. It's this interaction between the plasma and the field. So if some sort of forces cause the plasma to move in a certain way, like you have maybe high pressure here and low pressure there, the plasma is forced in this direction, for example. Other effects related to the rotation of the sun cause the plasma to move, and deep in the sun and even at the solar surface, the plasma dominates over the magnetic field. It's the opposite in the corona, but down low, the plasma dominates, so it just moves the magnetic field with it. I talked about the dragging at the endpoints of the coronal magnetic field lines when I showed that movie of the turbulence. So forces can move the plasma, and the magnetic field is stuck to the plasma, so you can amplify the field that way. And that is called a dynamo process. So it's the dynamo that modifies the sun's magnetic field in this 11-year solar cycle. It works on other stars. There's a dynamo happening in the core of the Earth as well. So it's this fundamental interaction between charged plasmas made of charged particles and magnetic fields. So much of this, basically all of this, boils down to that.
How long have you been able to collect this kind of data, like to be able to see the flares and the CMEs?
Yeah. Flares we can observe with visible light. So we've seen those for many, many years. I mean, this guy Carrington, who's that big event from 18 whatever was named after him, he was able to see a flare in visible light way back then. But a lot of the interesting emissions that reveal gases at higher temperatures are like the ultraviolet and the X-ray. And those do not get through the Earth's atmosphere. They get absorbed by the atmosphere, and hence we get these effects on communication. But that means the light doesn't get down to our telescopes on the ground. We can't see it. So in order to observe in those very interesting parts of the spectrum, we have to get above the Earth's atmosphere. So we have to have satellites. We put our telescopes on satellites. So the space age, started in, well, actually some V2 rockets captured by the Germans at the end of World War II were first used to study the sun in X-rays. Before working at Goddard Space Flight Center, I worked at the Naval Research Lab, which is also in DC. It's down by the Wilson Bridge. And in many ways, the whole field of space science, all of this, using observations from space, started with the Naval Research Lab. Because the military captured the German V2 rockets, the Naval Research Lab was in existence. Some of the scientists there said, hey, wouldn't it be great if we used those rockets to get above the atmosphere so we could look at the sun in X-rays? And they did that. And that was the start of space science.
Do you think that's how you'll, when you have enough data, do you think you'll be able to predict better based on what you're saying with how the scientists kind of found meteorology was 40 or 50 years ago? Do you have more data to model and predict?
I'm going to give you an extreme answer, then I'm going to explain it. Absolutely not. I actually have, it's because we need the theory to go along with the data. You need both of those to make progress. I have kind of a peeve with NASA, and I've been fighting with NASA for a lot of my career. NASA spends huge amounts of money launching these very expensive spacecraft. And they're doing great things. They're collecting great data. But only a tiny fraction of NASA's budget goes to pay scientists to analyze the data and develop the theoretical models and the physical understanding. I think in terms of increasing our understanding of the sun and everything in nature outside the surface of the Earth, I think it's not a proper balance. I think we should be spending more money paying for scientists to think about the data and develop the theories. Now still, we have to spend most of our money on getting new data because that's just inherently a much more expensive enterprise. So with new data, we'll do much better. That will be a big part of improving our forecasting. But without the theoretical efforts going hand in hand with the new data, we wouldn't make much progress.
Can I follow up on that? What are really the theoretical questions that we aren't understanding about the basic, magnetic field, plasma?
So many questions.
It seems like it's really a matter of getting more detailed data and more detailed models to predict sort of small-scale things, but it sounds like you're saying it's really some fundamental questions.
Yeah, there are. We have a very good handle on general aspects, and we have a very good handle on some details. But take this coronal heating problem, which is near and dear to me. The bit about the tangling of the field and breaking in small places and giving nanoflares. Just how that happens, we don't really understand. This basic process of reconnection of magnetic fields. You have two field lines that are that are misaligned. They come together. They break and reconnect with a partner from the other field line. This basic process of reconnection, which is so fundamental to so many of these phenomena, is not yet well understood. And we're making big progress, and it's mostly theoretical progress, because this happens on a tiny scale that we will never observe, even with an instrument with the most incredible spatial resolution. This happens on scales of sometimes centimeters. So we'll observe the consequences of that reconnection that are manifested in the larger scales, but to understand what's happening on the smaller scales, sort of driving everything, we have to have the theoretical modeling. And it's really exciting. I mean, it's fun. I kind of straddle between theory and observation because I think that's where you make the biggest progress. You know, some people do theory without ever thinking about observations. You know, they're kind of living in a black box. Other people just look at data, but they don't have a real good theoretical grasp, so they can't really get a deep understanding. I think if you do both, that's how you make the best progress. So that's kind of how I've directed my career.
I have a related question. Where do you think the next breakthrough is likely to occur in our understanding of space weather?
I would say one area is the initiation of coronal mass ejections. What causes them to go off? You know, we know that the magnetic field of the active region gets stressed and stressed and stressed, and then something causes it to break. And you know, we certainly have ideas, but we haven't yet really nailed that down. And once we nail that down, then we'll understand what causes flares, because I think it's pretty clear that the process that leads to coronal mass ejections leads shortly thereafterward to flares. So I have pretty high hopes that in the not too distant future we'll nail that one. And that will mean that we'll be able to predict before CMEs go off and before the flares go off that they will go off. And as I was saying before, some of these space weather consequences are so prompt that once it's happened, you're toast. You know, you have to predict them in advance. Okay.
Be respectful of your time.
Sure. This is great. Yeah, I really appreciate all these questions. Yeah, I think the two of you had the last two. Is that right?
Yeah.
But this lady has been very polite.
How frequently, not how frequently, but over the years, have you seen an increase in these storms? And so, do you know why?
Yeah, it's very much related to this issue of what causes the sun's magnetic field. this dynamo. So the solar cycle has the magnetic fields getting stronger and weaker and reversing polarity every 11 years. So it's primarily related to that. CMEs and flares are more frequent during the maximum of the solar cycle, less frequent during the minimum. And I should point out, this minimum that we're just coming out of now has been fascinating. It's been the deepest minimum we've known since the space age. In other words, the sun has been more quiet a couple of years ago than we've ever seen it in the space age. So we're trying to understand why that is.
Before I ask my question, I would just want to second what you said. I just came back from a conference that I thought had the greatest motto, which is, nothing is more practical than a good theory.
Very good.
My question is, what are the effects of space weather on human health?
Well, if you're out in space, not shielded by the magnetosphere, and these high-energy particles zap you, it can be bad. I mean, you can die quickly from radiation poisoning. You can die later from cancer. So that's why NASA needs to know about this, because if there's a prediction that there will be one of these storms, the astronauts can't be in a spacewalk. They have to go to a special part of their spaceship or the space station that's well shielded with thick metal that will stop the particles from hitting them. And so I worry a little bit with this commercial space flight. These are little spaceships that are going to go up and people are going to look around and fly back down. They don't really have plans, as far as I know, for any sort of shielded compartments. So they better not fly when there's a chance of one of these storms of high-energy particles.
What about here on Earth? When the sun is more active, are there noticeable health effects on people's health?
Not so much. I mean, if you're a flight attendant and you fly these polar routes, over the course of a year, you can get a really sizable dosage of radiation. So that is a little bit of a concern. But for most of us, not really. I mean, there's UV light coming from the sun all the time. It might go up temporarily during a flare, but most of the UV is absorbed by the atmosphere. But there's a question of global warming. Okay, let me just say this. The sun contributes to global warming. We have the 11-year solar cycle, but then the envelope of those solar cycles changes. So we've gone through periods where we've had many cycles in a row where the activity has not been very high. You may hear terms like the Maunder minimum. So we believe that the sun plays a role in climate change, but we also believe it's a very small role compared to the anthropogenic sources of climate change, what we humans do. But knowing what part is solar and what part is human is important to sort out.
Jim, thank you so much.
My pleasure. Thanks for all your very good questions, by the way.
I hope that you, like Ann and myself, when we went out to NASA, had a chance to now really understand what space physics is, and to see a real-world application. And I love the fact you put the John Stewart clip in there, because that also relates to our societal science and society goal in terms of how as scientists can we effectively communicate to a broader audience. And I think they should have picked Jim to go on stage because we can understand him. So, and he has enthusiasm. He was excited about what's happening. So thank you very much.
My pleasure.
You're very generous with your time. It doesn't look like you had a really bad week. It looks like you put it together quite quickly, and I know we're really grateful. And thank you for letting us videotape you as well, so that others can benefit.
Did the lens break? I don't know. Normally I do that. No, you're very welcome. It's a treat for me. Again, thanks for your attention and your very good questions.